This I'm going to explain distributed computations. So distributed computation is nothing but before the distributed systems is nothing but systems whose components are interconnected among the different networked computers. So these computers want to communicate with the help of passing the messages to one among. This is called as a distributed systems. So if I want to process any complex logics means the problem is written to member of small tasks. So these small tasks are given to the different network computers and passing the messages, and finally we can coordinate and get the results. This is called as a distributed systems. So in that we have distributed definitions. So distributed system definitions. A distributed system is a system whose components are located on different networked computers which communicate and coordinate their actions by passing the messages to one another. This is called as a distributed computation. Then distributed systems. So here we have features. So in the distributed computers, so no common physical clocks, and also does not share the memory. So no shared memory. Here we have graphical separations and autonomy and heterogeneity. These are the features of distributed systems. So and the next one, model of distributed computations. So in the distributed program, is a composed of set of asynchronous process that communicate by the message passing over the communication networks. So here the passing of messages based on asynchronous process. So each process may run on a different processor. So in the distributed computation, so each and every process run on different processors. So process execution and message transfers are asynchronous, and that this is called as a model of distributed computations. So in that so model of distributed execution means the execution of process consists of sequential executions actions. In the distributed networks, networked computers, we have n number of processes. These processes are executed based on the sequential execution of its actions. In that each and every process have some events, three types of events. The first one is internal events, so another one is a message send events, another is a message receive events. Each and every process have these three types of events. So first one internal events, and then second one message send events, and then third one message receive events. That means let EIX denote the X the event at the process PI. Here we have n number of process P, and then P have n number of events. The event is represented as event number is represented as X the event. That means EX. EI is nothing but ith process. That's a EIX. And also for another thing. For a message M, its send of M and receive of M denote its send and receive events respectively. The event at a process are linearly ordered by their order of occurrence. The execution of the process PI produces a sequence of events EI1, EI2, EI etc. EIX etc. EIX plus 1 and is denoted by HI, where HI is nothing but small hi binary relation I. HI is a set of events produced by the process PI. Here PI is nothing but one of the process. The process have n number of events. Thus n number of event is called as a HI. And then binary relation defines linear order on these events. In there, each and every event is performed based on linear ordering concepts. And the relation by linear order express casual differences among events of PI. Casual difference will be maintained among the n number of process. In the see the diagram, here we have a process timing diagram. Each and every process have n some events. Here we have three process P1. So P1 have 5 events: E11, E12, E13, etc. E15. Process P1 have 5 events, and also P2 have 6 events. So P3 have 4 events. In that this first event, the P1 is first event is called as internal events. Second event is called as a send event. As a process P1 want to communicate process P2 means it send the event E12 to the E22. That means E12 is nothing but a send event of process P1, and then E22 is a receive event of process P2. So likewise, it communicate the messages among the all the process. And also here P2 means P2 want to communicate P3 means it send the send event of E23. So E23 third event of process P2 will be sent to the second event. That means the second event of P3 process is receive events. So send event to receive events. And also if process any P1 process need some resources means the P3 send the event to the process P1. There's a P1 have receive events. P in the process P1 E14 is nothing but a receive events. In the process P3 E34 is nothing but a send event. And then here the process P1 E11 and then E13 are the internal events. C12 is nothing but a send events. This is called as a process timing diagrams. In that we have the send and receive events signify the flow of information between process and establish causal difference among the sender process to the receiver process. And then your relation binary relation messages capture the causal difference due to the message exchange in is defined as follows. For every message of M that is exchanged between two process, we have send of M binary relation message to receive of M. The relation defines causal difference between the pair of corresponding send and receive events. Here causal difference will be maintained pair of corresponding send event and receive events. And then we have causal precedency relations. In that order of messages is a partial ordering of message in a distributed computing environment. The distributed computing environment is nothing but interconnection of networked computers. Each and every computer want to communicate means passing the messages between one another. In that message, MI to process PK necessarily to produce the proceed the transmission of messages MJ to the same process. So the delivery takes place in the order of MI followed by MJ. In that MJ want to send the deliver the message means we after MI only it deliver the messages. That means MI followed by the MJ. And then here happen before relations. Happen before relations is nothing but as a local ordering. Then the A and B are two occur in the same process. Two events occur in the same process. The occurrence of A occurs before B. That means A tends to B. And then Lamport's ordering is happen before relations denoted by Lamport's law as follows: transitivity property. That means A, if A tends to B and B tends to C, then A tends to C. We can say A tends to D. That's called as transitivity property. And then model of communication networks. And then model of communication networks means there we have three types of three models. One is a first in, first out, and then non first in, first out, and then causal ordering. First in, first out is nothing but channel act as FIFO message queue. In the FIFO message queue, the message will be maintained in the queue. In that, the message will be delivered based on the first in, first out order messages. And the non-FIFO is nothing but non-FIFO. A channel acts like a sender process adds the messages and receiver removes in random order. Here, sender process receive the messages in one by one, and then receiver remove the messages in random order. That's called as a non-FIFO. It's not FIFO. The receiver receive the messages in random order. And then causal ordering. So causal ordering is something but it follow the Lamport's causal happen before relation. That's the Lamport's law. And then global state. A distributed snapshot represents the state in which the DS might have been. A snapshot is a single configuration of the systems. The types of states, there are two types of states. One is a consistent state and also inconsistent state. A consistent state is nothing but a message cannot be received if it was not sent. Such states are called as a consistent global states and are meaningful global states. That's called as a consistent state. And the inconsistent states is not meaningful in this sense. Since inconsistent global states are not meaningful in the sense, the distributed systems can never be an inconsistent states. So here you have example of cuts. So cuts is very important in the process communications. Here we have cut is nothing but a zigzag line joining the arbitrary point of the each and every processor line. That's called as a cuts. So in the space timing diagram of a distributed computation, a cut is a zigzag line joining one arbitrary point on each process lines. So P1 have 4 events. See the diagram, the timing diagram. So P1 have P1 have 4 events. That's E11, E12, E13, E14, and then P2 have 4 events. So E21, E22, E23, E24. Also same P3 also have 5 events, and then P4 also have 2 events. So here we have the cut C1. That's a cut is in the cut is nothing but the in the phase timing diagram. So left side of the cut is called as a past, and right side of the cut is called as a future. Here the C1 is nothing but inconsistent states. That means the message event is transferred from future to past. It's not possible, so it's called as a inconsistent states. You want to transfer the messages future to past is not possible, so it's a inconsistent states. And then consistent cut is C2 is a consistent cut. In that the left side of cut is called as a past, and right side of the cut is called future. Here we are sending the message from past to future. It's possible, so it's called as a consistent cuts. So here we have two cuts. One is a C1 and C2. C1 is inconsistent cut, and then C2 is called consistent cut. So this is a cut information, the process timing diagram. Here we have a cut slice space timing diagram, and there's the set of events in the distributed computation into fast and futures. The fast contain all the events to the left of the cut, and future contains all the events to the right of the cut. For a cut C, let past of C and future of C denotes the set of events in the past and future of C respectively. In a consistent cut, every messages received in the past of the cut was sent in the past of the cut. In already we have discussed in the figure. C2 is nothing but a consistent cuts. We are sending the messages from past to future. We are receiving the message from past. That's called it's possible. So it's called as a consistent cut. So another one, all messages that occurs the cut from the past to the future are in transit in the corresponding consistent global states. A cut is inconsistent if message crosses the cut from the future to the past. If message is crossed between future to past, means it's not possible. It's called as a inconsistent cut. So here we have a diagram. This diagram. So we have C1 is the inconsistent cuts. The message is passed between future to past. So future to past is not possible. So it's called as a inconsistent cut. So cut is have two types. One is a C1 as a consistent cut, and also inconsistent cuts. And then we have a past and future counts of an events. An event EJ would have been affected only by all events such that EA tends to EJ. That's here we have the diagram. This is a cut of left of the port cut is called as a past, and then right of the cut is called as a future. And then maximum past of I is equal to EJ, and the maximum future I equal to EJ. These are the past and future counts of an event. Here we have all such events. EA belongs to the past of EJ. EA in EJ. Here let past of EJ denote all the events in the past of EJ in the computation. So H and then binary then. So past of EJ is EJ equal to for EA for all EA belongs to H, and then EA belongs to H. That means EA tends to EJ. The future of an event EJ denoted by the future of EJ contains all the events EA that are causally affected by EJ. That means in computation, X binary relation, future of EJ is defined as, so future of EJ equal to EA for all EA belongs to H, and then EJ tends to EA. This is the concept of past and future counts of an event. So very important. So cut is very important because cut is nothing but a zigzag line joining the arbitrary point of the process diagram. In that we have past and future. Here we have two types of cuts. One is a consistent cut, another one is an inconsistent cut. Okay, and then consistent cut means the message is message crossed between past to future is a consistent cut. So inconsistent cut means message crosses between from future to past. It's not possible, so it's an inconsistent cut. This is a diagram for past and future counts of an event, and then this past of EJ, and then future of EJ is y is nothing but EA tends to EJ, and then EJ tends to EA. Okay, and then that's all. Thank you.